People wonder why a microphone guy is involved in airborne noise and acoustics. Well, my company makes microphones, and we also are really concerned with the perception of noise. Why? Well, microphones make noise. There's been a lot of work done in the past decades on quantifying undesired sound in the presence of desired sound, which is kind of the definition of noise. And we get to beat up on that a little bit. I'm a private pilot and a home builder, and so I've been talking with Mark Moore over the years about, well, what can we do to make this new vertical flight ecosystem a reality in the community that has to accept it. So part of that is an acoustic challenge, and so I've been sort of leading the discussion, starting with some work that I did for Mark at NASA, and then subsequently kind of heading the acoustics project at Elevate to try and inform ourselves on what we might be able to do in designing new aircraft to be perceived as quiet in the community. And it's really a heady time to be involved in this kind of industry, because for the first time we get to develop a new aerial ecosystem with community noise as a driving force, which is, some of us think, really important. What are we pressing here? There we go. So we want to do some analysis, basic napkin sketch stage of why aircraft are noisy, what we can do to drive design, and what we can do to measure the results as we progress a design. We first of all have the actual physical noise that's generated by motion of the air from the rotor structure, propulsors, whatever they are, the airframe, interaction with the ground, and so on. We can measure the pressure waves that are generated by that. We can also measure, with some new tools from the past very few years, the physiological response to that pressure wave that informs our brain as to how loud it is. We also have a separate problem when an aircraft operates in a community that my friend John Leverton calls virtual noise. And that's where people have other non-acoustic responses to the aircraft's presence and operation that they use noise as a proxy for. We can't help much with that. The whole effort has to be involved there. But we can work on the noise part. To talk a little bit about the virtual noise issue, here's a slide from some work that was done in the Netherlands a few years ago that basically sets up the question, well, we want to measure how noisy things are. Well, we'll use the day-night level, which is an A-weighted sound pressure level averaged over the day. And we say, right, these things shouldn't be louder than a certain amount in order to achieve a certain amount of annoyance in the community. Well, you look at three sets of curves there. The top curve is the amount of noise that is necessary to have that percentage of people highly annoyed. So you'll see for the air side that 60 DNL levels from an airport operation results in about 65% of the population being highly annoyed. The top curve is highly annoyed. About 30% of them are somewhat annoyed. That's the middle curve. And I'm sorry, I have that one. That's right. And the bottom curve is that about 15% of them are slightly annoyed. How come there's so much difference between the air curves and the road curves? and even more of a difference with the railway curves. That 60 dNL noise level produces some annoyance for only 5%, and only 25% or so are highly annoyed by that same exposure level, which is the best metric that we have today for railway noise. Well, we call this difference virtual noise, or the railway bonus is what it's called in Europe. In my opinion, there are two things going on here. One is a psychological weighting of noise based on source. People are not afraid of railways. They don't resent railways. All of the other emotional baggage. The other part, and the part that we can do something about, is that we're not measuring the noise properly. And so most of the rest of our discussion and our two esteemed panelists who will be joining here are about predicting and measuring the noise a little bit more accurately. More, and by accurate, I mean a closer correlation with the human response. We can measure the sound pressure. That's pretty easy. The time pressure history of the waveform being emitted by the aircraft, we can measure. The propagation through the air, we can predict very reliably. We can reconstruct the pressure at the listener's eardrum. Good. We can measure now, we have much better metrics for determining how loud the brain determines that signal to be. And that is a physiological measurement, physiological replica of human hearing rather than a subjective judgment. Loudness is not sound pressure. Loudness, although it's a very important component of annoyance, is not annoyance either. That's the first thing to remember. When we are asking you to measure the loudness of an aircraft, it is not a subjective measure. We know that it depends on frequency. There are certain frequencies that we are more sensitive to than others. Okay, so we have a frequency correction. It depends on the time structure. These aircraft, it's very easy to measure the loudness of a jet aircraft, for example, because it's a fairly constant sound. Helicopters, particularly, burst of sound than a constant sound. We say that the integration time of human hearing for onset is on the order of 1/10 of a second. That would be fine, except that the sound level measurements that we make for airports have an integration time of a second. And you can do the math and realize that short impulses are going to be louder than their long time averaged measurement would indicate. But we're getting to a little bit more smarts about measuring the exact partial loudness of the aircraft. That is, how much loudness is an aircraft contributing to an urban environment? And this is new work that has been done for other kinds of noise sources, but not so much in the past for aircraft. And Uber is actually funding and pushing a lot of new work in this area together with with Cambridge University, where some of the major workers in this field are doing their research. It depends on background masking. We're trying to figure out how much noise from the aircraft is audible to the person on the ground. And that depends very much on what the background sound is. So we can't really measure the impact unless we know what the background is. So we measure the background spectrum. We calculate the loudness in each equivalent rectangular band, which is similar to, in many cases, close to 1/3 octave bands. And then from that, we are able to predict the detectability radius of the aircraft that we're talking about. This then gives us a really actionable number of how far away can we hear this aircraft. And as we are beginning to establish some characteristic background sound spectra, we can then say that in a typical urban environment, this aircraft is going to be audible over this much of a radius during its takeoff, during its landing, and for its overflight at a certain altitude. From that, we can determine where there's going to be an acoustic impact on the ground. And that is, we hope, going to advance our ability to predict where there's going to be opposition or acceptability of that aircraft in the community. If we want to improve the acceptability in the community, we need to measure directly the factors that influence that. So that's my very brief presentation on a slice of the challenge, our response to the challenge that I think we all know about, and you can look forward to some improvements in that field in the coming years as we advance. And nearly all of this is going to be completely open, funded by Uber, but around the world for people to incorporate into their own research. We're really honored to have two other major contributors to the field of aircraft noise and aeroacoustics joining us. Professor Ken Brentner from Penn State is going to talk about some of the tools that have been developed to answer the challenge of how do we predict some of the noise on the ground from given rotorcraft and other kinds of aircraft structures. One of the last very original thinkers and serious leading lights in this field was Ferry Farasat at NASA, and Dr. Brentner worked with Dr. Farasat for a number of years, and I would say is the keeper of the flame, right, Ken? And he's leads the aeroacoustics program at Penn State. Ken.
Thank you. I guess the microphone works, or both of them work.
The microphone should work, and there's your slide set. Great.
Okay. I found the picture online so I could fit into the conference there. It's a nice picture, Alex. I like your aircraft. So let's see if I can work this. I tried to follow what David said about tools. I'm going to focus on the modeling and a little bit of background. I'm a professor. If it gets into too much detail, just sit back and try to be comfortable that there's a lot of detail that some people can really get into, and we need that. And don't worry about it if you follow it all today. And I'll try to give the main idea. So I'm going to talk about noise prediction. I'll first talk about the rotor noise sources, because we've heard a lot about acoustics, but with not much detail. We need to do the detail. I'm going to talk about some of the approaches. I will have a slide or two about some of the tools available, because I know that's important. And if I have a little bit of time, I want to show some slides from a talk earlier in the week that we presented, and just give you some examples of why things are important. So there's really several different rotor noise sources. I'll start out, I say rotor a lot because I've worked a lot on helicopter noise, but it's any rotating blades. I've worked on wind turbines, some propellers, and we can divide the noise up into, I guess the pointer only works up here, so I'll go on the left-hand side. Discrete frequency noise sources, things that can be represented by a harmonic series, and broadband noise sources, things that are not necessarily periodic. Thickness noise we talk about The way we calculate thickness noise, it's really like thickness of the blade in linear aerodynamics. It's only related to the fact that the air has to get out of the way of the blade, so it's the blade geometry in motion. Then there's loading noise, so the fact that we have a distribution of forces on the surface, and they're accelerating. They're accelerating even on a steady, if it's steady in the blade frame of reference, because it's rotating. So that acceleration causes noise. That includes things like blade vortex interaction or any kind of unsteadiness. All of that's really included in loading noise, but often we separate out the calculation of the loading separately and we call it other things. We don't have to worry about it much in this audience, but in helicopters we have high-speed impulsive noise where we have shocks and things. You guys don't want to do that. Please don't go there. That's really annoying. And then we have broadband noise. I'm not going to talk about that much in this presentation, but I think it's important and it's something we need. It's non-deterministic loading noise, and it can be from different sources like turbulence ingestion. That can be from the atmospheric turbulence. It could also be from turbulence off of the aircraft somewhere else or interference. That's not how people normally think about it, but I want to include that. But also self-noise sources where we have turbulence in the boundary layer going past the trailing edge, vortex shedding off the trailing edge, things like that. There's a whole host of them that Tom Brooks at NASA Langley looked at. Blade-wake interaction, where it's hip vortices or wakes interact with the boundary layer, with the blade, and we get an unsteady stochastic loading. Okay. For a helicopter example, these noise sources have different radiation directions. Loading noise tends to radiate, let me say, along the axis of the propeller, the axis of the rotor, but below, a helicopter below, so loading and broadband noise, where thickness noise tends to, for an edgewise rotor, ahead of the rotor. This is because of Doppler amplification that's ahead of the rotor in an edgewise rotor. And then blade vortex interaction noise or any kind of impulsive loading can have a directional nature. So these are just one type of unsteady loading. The unsteady loading noise tends to be very important and maybe the dominant noise source. I'll show you that for low tip speeds. And that's more relevant for what we probably want to do on these vehicles. Here I just put another example. This is sort of a classic example. This is from Guten's paper back in, I think, the 1930s. This was like one of the first papers on propeller noise, loading noise. It looks a little different because I flipped it to have the flight direction. But other than that, this is the prediction, and this was measurements back then. And so this is the plane of the propeller, and you can see a lobe of noise in this direction, nearly zero along the axis of the propeller. This is just the directivity for a propeller, which I thought I'd put in. So what are some practical approaches? I wanted to try to address what David said. And well, we can do analysis. I think analysis can work. It's simple things. Mathematical approaches are useful to achieve results, but probably too simplistic generally, especially when we have complex vehicles and multiple rotors. And I usually don't work at this level very much. There's semi-empirical analysis tools. These are quite useful. I'm not against these at all. They're very fast. But they require some basis, some database of experimental data that form their foundation or theory. So they're not necessarily valid for new configurations, and the configurations for the vehicles we're talking about are very new. They're not much like helicopters, for example. So for one case I referenced here, for helicopters, there's a paper by Pegg that has a whole set of empirical models that are very useful, and I use the broadband noise model. Other people could use these, so that's a good source, but it's probably not valid for anything that doesn't look like a helicopter. Even a large helicopter, they're probably not valid. I haven't looked at that. Then there's computational methods. I'm going to say integral methods generally, acoustic analogy and Kirchhoff method. We won't talk much about this. They can all be done by this. And then direct computations. That's direction. So it should be direct computations. So let me talk about this. I've got equations. These are just sort of schematic equations. You can look at the pictures and get the idea. In the acoustic analogy, this was originated by Lighthill. Sir James Lighthill started the field of aeroacoustics. And the idea was to have a wave equation and rearrange the governing equations so the source, everything else was a source term. And Fox Williams and Hawkins, Fox Williams was my PhD advisor at Cambridge, they rearranged it so that, or they put in surfaces so we could have a surface term. So that includes all of the source terms. And how we practically do it is we don't include the volume source terms, and we just include the actual surface of the blades and the loading on those surfaces. Now, there's another way to do it, a Kirchhoff approach or a permeable surface, Fox Williams Hawkins I call it. If you take CFD data typically and you put it on some surface, a fictitious surface, so you have all the unsteady loading, it's got to have all the acoustics in it and the flow field, then you can calculate, propagate the sound outside of that surface. So if you have a very complex flow inside and very good CFD, CAA, computational air acoustics, you can calculate the flow outside, and we can do that, but it's more expensive to get the flow right. And of course, you can use in direct computation, you can use CFD if you're a very accurate CFD and propagate the sound. It's just part of the fluid mechanics, but it's difficult, and you can't go very far. And errors accumulate as they propagate, so you have to use high order methods, and you can't propagate very far. You certainly can't go to certification microphone locations and things like that. So this is what we use mostly. And that's what I'll be showing you. So this is the Fox-Williams-Hawkins equation. I already talked about it, so I won't talk about it. The way we really do it, though, is an integral formulation. This is called Faraset's formulation 1A. What I want to show you, don't worry about the formulation, I just want to show you the colors. We have velocity terms here in blue. R is the distance from the observer. Don't know what, I must be clicking it. So we need things about the motion. We need the loading in the green here, the L terms. And that's the kind of, so you need blade motion and loading and their time derivatives as input. That's the kind of things the community needs to provide from their analysis tool, their aerodynamic analysis tool, and they generally have that. Okay? So, what kind of prediction tools are available? This is directly answering the question David posed to me. Well, I think this is available. I haven't checked. I looked online. ANOP propeller analysis system, I see people using it in papers, Stanford and Langley. I'm pretty sure it's available, but this is US release only. Here's the website you can go look at and make contact with NASA Langley. Does anybody from Langley know, is this actually still available, the system? Yes, good, thank you. I know ANOP's available. I'm not sure about this. This is a fairly simple system, but for propellers it works quite well. Then PSU WOP-WOP is my tool that I developed at Penn State. I developed the WOP-WOP tool at NASA, but don't use that if it's out there anywhere, because this is a lot better, and that would be US only if anybody's got it, the NASA version. This is completely new code, not related to the NASA version. This is a numerical implementation of Faraset's formulation 1A. It's not rotor specific. It's very general motions possible. Multiple rotors are no problem, structured or unstructured grid input. We reformat the input to binary files for WOP-WOP, permeable or impermeable surfaces. I can do multiple observers in parallel, so we can do large computations pretty quickly. It needs to be coupled with analysis tools. It doesn't calculate the blade loads and all of that. You have to get the unsteady loading, or the steady and unsteady loading from somewhere else, and the blade motion for that matter. So it's not an independent tool. And it's a research code. It's documented somewhat. It's not supported other than what I can help you with. An executable version is available for Windows that I distribute when I have time. Dan Walkspress at Continuum Dynamics has it coupled with Charm. We worked together and coupled it. He does have a license to be able to distribute this executable version. It's not supported either, but he can distribute it with Charm so that you can run the whole system together, and he has some support. He knows how to run it with Charm, so that's another place you can get it. Now I want to show you, I don't know how I'm doing, how am I doing on time? Okay, another minute? Okay, well I want to show you a case where we did an unsteady propeller calculation, just to show you a couple things. I won't go into how we calculated the loads, but we used a simple loading code earlier this week. And here this is the propeller. This is the overall sound pressure level, thickness and loading noise, red and blue, and the total in black. Axis of the propeller. This is steady loading, and you see we get the blue line is like I showed you before. This is at Mach 0.7 case. But when we put this at angle of attack, 2 degrees angle of attack, so we have unsteady loading, very simple loading, quasi-steady, we get a big increase in the noise along the axis. That's something this community needs to pay attention to. Okay, so unsteady loading is important. Then we looked at different tip Mach numbers. We don't think 0.7 is the right one. We want to go down to 0.4 probably, or even lower. But you have to redesign the propeller to be able to do the same job, because we want to go the same speed, the same thrust. So we have more blades and different solidity. Well, what happens at 0 angle of attack is you get a lot less noise when you lower the tip speed. Okay, and that's what people expect. And the thickness noise goes down faster than loading noise. So the noise sources change with tip Mach number. But as soon as I put in unsteady loading, here's the bad news. I do get that increase along the propeller axis, but it doesn't go down very fast with reducing the tip Mach number. That unsteady loading is a problem. So I don't get the effect of reduced tip Mach number as much if I have any unsteady loading, and you almost always have some unsteady loading. Okay, at a higher degree of angle attack, same thing. If you have more blades, here's the same setup. I went from 4 blades to 6 to 8. I'm not saying these are practical propellers, but they have different distribution of chord, basically. And they're on each of these angles of attack. Increasing the number of blades from 4 to 6 to 8 decreases the noise a lot. Big benefit. And that benefit's true even with unsteady loading. That's good news. That's something you can use. Okay, what about multiple propellers? Lots of propellers on these vehicles. What we did is we started out with 2 propellers. The previous ones were all just for 1 propeller, but so we had a vehicle like this, and we said, well, we'll take those. We'll use 1 propeller or 4 or 6. They're not optimally placed or anything, but we kept the tip speed the same, all Mach 0.4, all low tip speed, and we kept the area the same for the total of all the propellers, and they all have the same total thrust. And at 0 angle of attack, looking from the side, well, they're all about the same noise. That's what people kind of expect. But when we have unsteady loading, this is not good. We get about a 20 dB increase in noise when we go from 1 propeller to 2 and 4 and 6. I'm not saying that's always going to happen to 20 dB, but that's a big increase we've got to pay attention to. At higher angle of attack, it gets spread out a little bit more. 1 propeller is less. 2 propellers is not quite as much as 4 and 6. So we get a big penalty for multiple propellers doing the same job when we have unsteady loading. All it says is we've got to really pay attention. There's really challenges here, and some of these simple ideas of just making the tip Mach number lower may not always help. So there's not as much experience with low tip speed in the literature. There's some, but not as much. Broadband noise, I think, could be important. I've not talked about it. That doesn't mean I don't think it's important, but the tools aren't as well developed. Aerodynamic interactions between rotors and the airframe could lead to excess noise, extra unsteadiness. We did angle attack just as a simplest case of unsteady loading. And prediction tools are available, but I think you have to have some expertise to use these things. And some of that expertise is the loading that goes into them, but there's also expertise in understanding what you're getting out. Is it valid? And so I think that sums it up. This isn't quite relevant to the conference, but I love the picture. It's actually from the Super Bowl time frame, so.
Thanks very much, Ken. That's really important.
All right, great, thank you. So I'm gonna take this maybe in a little bit of a different direction, talk a bit about how we might reduce the noise of these vehicles in operation, and I guess we'll get started here. So Ken did an excellent job kind of setting up the major noise sources, so I'm not gonna go over that and belabor that point, other than to say, for just like regular helicopters, these new class of vehicles, we expect most of the noise is going to come from the rotors. The steady sources of rotor harmonic noise can be pretty effectively reduced by tip speed reductions, but we know that this is not going to be nearly as effective for unsteady sources of noise. And you showed some examples of changes in angles of attack, but there's lots of other sources of unsteadiness. Blade vortex interaction, which we worry about a lot from helicopters. It's where rotor blades are interacting with the vortices from the rotor wake. That could be a wake from the same rotor, but in the case of many of these vehicles, it could be a wake from other rotors on the vehicle. That causes a rapid fluctuation of air loads on the rotor blades, results in an impulsive and very annoying source of noise. But we can also get other sources of unsteady noise, interactions between the rotors and the structures, the wings on tilt wing vehicles, stators, if you put the rotor in a duct, the duct lip, you can get shedding off of that. And again, tip speed is not necessarily the way out here. So we need to look at something else. How can we avoid these sources of noise from occurring? Well, lots of other people have, over the decades, have kind of shown that the rotor noise, say for an isolated rotor, it has a unique correspondence to the operating condition of the rotor. If we change the operating condition of the rotor, we can make big changes in the noise radiation of that rotor. So these different parameters are closely linked to the performance parameters that you would usually use to characterize the operating condition of a rotor or propeller. It's, like I said, it's a set of 4 that we'd use for a conventional isolated rotor. If you have other rotors or aerodynamic bodies in that environment, you may have to add 1 or 2 other parameters in order to actually capture that variation. So what do we do today in order to try to guide helicopter pilots to low noise operations? Well, while a lot of these design tools are very useful for predicting the noise of a vehicle that we don't have yet, we don't yet have the validated accuracy where we can use them to design low noise operations effectively. So what we do is we take measurements, and we'll fly the helicopter over an array of microphones, repeat that for a variety of flight conditions, typically different airspeeds, descent rates, and then use that data to build a database that represents the magnitude and directivity and frequency of the noise as a function of the rotor operating condition. And then basically we identify which states in there are noisy, and we tell the operators, hey, stay away from flying in those positions. Now, our models, they're empirical because they come from measured data, and just like any old empirical model, we can't get out of that empirical model anything that we didn't put into it originally. So, what do we want to do when we want to handle unsteady flight conditions that we didn't measure, where the operating condition might change a lot? Changes in the configuration of the vehicle, weight, drag, payload, other effectors that we have on that. And then variations in the ambient conditions, the density, temperature. They're all going to change these aerodynamics of the vehicle. We know that. And we expect that they change the aerodynamically generated noise. So one way out of this that I've been working on is what I call FRAME, Fundamental Rotorcraft Acoustic Modeling from Experiments. And I'm not going to go into all the details here, but the basic idea is that we can have a relatively low fidelity computational model of the aerodynamics and acoustics of the rotors that are important to us. And we then, because that model is relatively simple, we can invert it. And we can tune it to measured data that we get for isolated rotors in wind tunnels, or even rotor data that we can extract from flight test data. What we end up now is a analytical model that we can use to explore the noise radiation in different operating conditions, but it's basically grounded in and retains a lot of the accuracy that we got from our empirical modeling. So that gives us some confidence that the predictions we make at other operating conditions are going to be reasonably accurate. Now that we have this model, there's lots of cool things we can do with it. So I'll give you one example here very briefly. We could take, say, measurements from 3 different flight conditions, comparable to maybe what you'd do for noise certification for a helicopter. And then we can use that noise data in order to generate noise information for hundreds, even thousands of different operating conditions that there's no way we could practically measure. Once we have this kind of data now, we can now model what the helicopter does during the variation of the operating conditions. So for instance, I alluded to before, helicopter goes into a maneuver. The main rotor of the helicopter is going to rapidly go through a bunch of different operating states. You can see down here on the bottom of this chart, there are 2 plots that give you time histories of the noise levels of, in this case, a Bell 430 helicopter during a couple different maneuvers, a pitch up and a roll. And as that maneuver starts, in both cases, you'll see that the noise levels rapidly increase. On an order of, say, 10 dB, which that might sound to you twice as loud. And if you think about it in terms of maybe a noise footprint, that could be a noise footprint that has 10 times the area. It might be annoying 10 times as many people if you allow the rotor to get in this kind of operating condition. And our conventional models, they're based on empirical data, don't model this whatsoever, but you can see using this kind of approach with the red line, we get pretty good agreement between that and what happens. So now we have this capability, what can we do in order to influence helicopter operations and other rotorcraft operations to reduce noise? So one idea is to give the pilot some real-time feedback as to the current noise emission of the vehicle. This model is relatively lightweight, so we can run it in real time. In fact, much faster than real time. It'll run on my cell phone. And this is just sort of a initial prototype that we put together, but we're showing there noise footprint, for lack of a better metric at this time, just 65 dBA noise footprint. We're going, people will be noised inside that region. I'm not going to get into details of it now, but on the side there on the right, we have sort of an indication. Because we know quite a bit about the aerodynamics of the vehicle, we can give some indication, some guidance to pilots as to what they can do to reduce noise. So I'm going to ignore that guidance, actually. We're going to start a little video here, and this is going to show just a turning, descending flight condition. So as the helicopter turns, this is all being computed in real time, was when I made the video, you see that large increase in the annoyance footprint from that vehicle as the wake passes up through the rotor. And again, now as we start to exit this descending flight condition, we're going to bring the wake back into the rotor, and you're seeing a very, very significant increase in noise, which should scare you a little bit, that any maneuver, anything you do to pull these vehicles off condition can lead to very substantial increases in noise radiation. So, one thing that we can do, now that we have a relatively lightweight and quick model, is that we can try to look and see, through kind of tailored operations where we try to control the rotor state, how much of a noise reduction could we get? So, shown here on the right are a couple of different noise footprints. The one on the top is sort of just a typical, going in from cruise to do a turning approach to a landing. And on the bottom is the same thing, but with an optimized flight procedure that's developed using this kind of noise model. And you can see we can get a very, very significant reduction in the area that's affected by the helicopter's noise by just changing the flight trajectory in order to control the rotor's acoustic state. Now, I think for practical purposes, for a lot of these vehicles, these sorts of flight procedures are going to have to be developed at the time of use. You don't know necessarily in advance what the ambient conditions are. You don't necessarily know how the vehicle is going to be configured, what the payload is. Certainly other air traffic and weather can pop up that cause you to change your flight plans. So you need to be able to come up with a very timely estimate of what you should do next. And I think, right now we're in the part where this kind of noise modeling is fast enough that if we combine it with some sort of greedy optimization algorithms, we can generate effective flight guidance on the fly, which can be given to our pilot, or it could be passed into a flight control system that'll fly these sorts of profiles for us. One last thing I wanted to talk about is that especially most rotorcraft, have lots of excess degrees, or some excess degrees of freedom. Even from a single main rotor conventional helicopter, you have at least one. As you start to add, of course, more propellers and rotors and flaps, you end up with lots of different degrees of freedom that you can exploit in order to control the acoustic state of your different rotors and hopefully end up minimizing noise on the ground. So one kind of quick example here is from the XV-15 tilt rotor. shown in the lower left in that photograph. On the right are contour plots that show the radiated noise for the vehicle. And both of these are for nominally the same flight condition, 70 knots indicated airspeed, a 6-degree rate of descent. The top plot there is when the rotor nacelles are closer to helicopter mode at 80-degree nacelle angle. And we see you get that big bright red hot spot where you have a large amount of blade vortex interaction noise. If you bring those nacelles down more towards a conversion mode, kind of shown like in that photograph there to 60 degrees, you can almost completely eliminate that blade vortex interaction noise just by making a configuration change in the vehicle, even though you're following essentially the same flight trajectory. Now I'll warn you, so some of these different trim states that you might put the vehicle into, they may result in noise reductions which are not global, just directional. I mean, here's one example. You might even get noise increases in certain directions. And of course, passenger comfort or vehicle performance may be compromised as you try to optimize for acoustics. This is a lot of things for the pilot to handle at once, especially as we increase the number of degrees of freedom. But if we build some acoustic knowledge into our flight control system, it can potentially offload the pilot and handle balancing performance of the vehicle that we expect from the acoustic emissions. So just to sort of summarize, I mean, we have the capability to do real-time noise modeling today, and we can use it. This modeling can be used right now to give some pilots some intuition about the acoustic characteristics of their vehicles, how to fly more quietly. But we can also use that to develop guidance for pilots to perform tailored operations to reduce noise, to control the configuration of the vehicle in order to minimize its acoustic state, and ideally to avoid increasing pilot workload. And what enables this really is increased autonomy. It's going to allow us to include some acoustic considerations in how we operate the vehicle. That could just be fly along the pilot's intended trajectory at the quietest possible way, or maybe you just hand everything over to the vehicle and then flies optimally and along the quietest possible trajectory. Okay, so that's all I have, so thank you very much.